Our goal for today is to start talking about the ideas of differentiability and tangent planes and a lot of various notions from single variable calculus. If you're comfortable with the ideas in single variable calculus, you'll see that many of them translate in a very nice way. And if you're not comfortable, well, now is a great time to start thinking about them so that we can become comfortable. Well, there's a lot to do, so let's begin. Our starting point is talking about the notion of differentiable. Now, when we go back to single variable calculus, we say, oh, differentiable means we have a derivative. And so if the function has a derivative, we say it's differentiable and vice versa. Well, there's actually sort of a better notion of differentiable. And that is to say, hey, locally, it looks flat. In other words, if you zoom in and zoom in and zoom in, that it becomes more and more like a line if we're doing a function of a single variable. Now the question, is that still true? Well, what do we have? We have these partial derivatives. So things like partial f, partial x, partial f, partial y. If we have those partial derivatives and they exist, locally do we look flat? The answer is actually no. It's a little bit more subtle. So why not? Well, a nice example can illustrate what happens. You see, suppose you have the function square root absolute value of x, absolute value of y. This is a perfectly fine function defined for all values of x and y. Now, what happens? Well, if you were to go and plot it, this is actually a picture of it, which is reasonable-ish. You can get more reasonable, of course. Computers are really good at plotting stuff these days. But what happens is you say, okay, suppose we look at x equals 0. What's true? Well, when we look at x equals 0, then our function is just always 0. And so that says, hey, I'm identically 0 along that axis. If we look at y equals 0, again, our function is identically 0. So these correspond in this picture to these two axes here. And now we're like, oh, see, when we look at just those slices, you say, look, the function is always 0, so the partial derivatives are 0. They exist, and they're very nice. You say, okay, well, what is that suggesting we should look like? Well, it's suggesting we should look more or less very flat. We should look like the xy plane. That's sort of the suggestion. Now the question is, does this curve look like the xy plane? And the answer is no, it doesn't. Okay, well, first off, I should correct myself. I said curve, I should have said surface. How can we see that? Well, let's slice in a different way. Suppose we were to slice not at something like y equals 0 or x equals 0, but along y equals x, so at a 45-degree angle. So what we see is along the line y equals x, we get that our function becomes the square root absolute value of x, absolute value of x, which means it looks like the absolute value function. In other words, it's a v. And the thing is, no matter how close you zoom in on a v, it's always going to look like a v. So this is a little bit pointy at 0 and can't be flat. So no matter how far you zoom in, it will never be flat. Okay, so it says differentiability, it's a little more subtle. So our goal is to say we want things to be flat. Now the good news is all hope is not lost, because this is kind of a bad function. You can imagine that when you try to take derivatives here, bad things happen at 0. So it turns out that we can recover if we add a little bit extra. So what's our little bit extra? We say, look, it's not just that we have fx and fy, but they have to be well behaved in the following sense. If we're near the point, the functions fx and fy are continuous. Now, if we add that condition, then we're good to go. So our rule of thumb is our function will be flat wherever our partial derivatives are continuous. Wonderful. Great. So how do we do that? Well, it's not so hard. We say, let's think about our function. We can look at f of x, y minus f of ab. So that's saying, let's look at the change of what's happening. So picture-wise, you can say, look, I'm trying to understand what's happening to the function at the point AB. So at point AB, it has some value. And now, when we talk about f of xy, we're really talking about, well, suppose you're near this point AB. So maybe here's this point xy near AB, and we're trying to understand what's happening to that point. So the difference is the difference in the outputs. You can think of it as the difference in your z values. Well, the challenge here is to say, wait a second, you kind of have two things changing simultaneously, x versus a and y versus b. And two things changing at the same time is a little bit tricky. So what we're going to do is like, whoa, okay, let's do sort of an intermediate step where we change only one thing and then we'll change the other thing. So instead of changing two things at the same time, we'll change one and then change the other. That's the idea. So how do we do it? Well, we're going to add a term in the middle where we just change one piece. So f of xy minus f of xb, and then we're going to put f of xb minus f of ab. You'll notice these two terms, f of xb, cancel out. So we've added 0. And it's okay to add 0. You can add 0 as much as you want. You won't change your value. But now we say, what's going on here? You see, this is looking in a slice. The slice when y equals b. So this is approximately the change with respect to x, that's what the f sub x is, at the point AB times the change in x. So there's a rate of change times an amount of change in the input. That gives it an approximation for the change in the output. A similar thing happens here. There's just a little extra step. We say, okay, now this is f sub y, because we're looking at how does y change in our slice at some x. Okay, f sub y, xp, rate of change with respect to y, amount of change in the input gives us a change in our output. But we have to be a little bit careful here. We say, yeah, that's f sub y at xp. Aha, here's our great, but our function's partial derivatives are continuous. So since x is close to a, this partial derivative at xb is very close to the partial derivative at ab. And so, what do we have? We have the following. Our function at xy is approximately f of ab plus, and that's coming from here, the change in x at ab times the amount of change in x. So there's a rate of change times the amount of change, and then a change in y, right? A rate of change with respect to y, amount of change in y. So what do we have? Well, we look at it, we say our function, this is our function, that's our left-hand side, is approximately acting in the following way. It's acting like this part right here. But now, if you look at it, what's the key? This part is flat because it's a plane. And you can stare at it because what's happening? Where are the variables? There's actually just two of them, and we can mark them. So there's an x and there's a y. And so what you have is some multiple times x, another multiple times y, and then everything else is a constant. That means it's a plane. So, of course, there's not just any plane. We have a name for it. It's the tangent plane. And another way to think about it is that the tangent plane is the best plane that gives information about the function. Now, we have to decide, what do we mean when we say it's the best one? Well, in particular, we have the nice following fact. So, what we can say is there's really three pieces of information that a tangent plane stores. So if I have a tangent plane at the point AB, then what have I really got? What's the information that I have? Well, then that means I have the following things. I understand what is the value of the function at AB, what is the partial derivative with respect to x at AB, and what is the partial derivative with respect to y at AB. If I know these three pieces of information, I get the plane. If I have the plane, I can recover these three pieces of information. Now, in one direction, it's not so bad, right? Because if we see we have this information, we can write down our formula for our plane. Life is good. Well, how do you go from a tangent plane to get this information? Well, we say, look, write it as z equals something. So we have z equals something times x plus something times y plus a number. Now, you want to know the function in AB, plug in a and b, and that gives you what the value is. So in other words, we're plugging it into the tangent plane. If you want to know the partial derivatives, look at the multiple that goes in front of the x, that's the partial derivative with respect to x. Whatever is in front of the y, that's the partial derivative with respect to y. And therefore, we can hop back and forth. So tangent planes store information about a function, and in particular, are three pieces of information. So in general, what do we have? Well, we can talk about the following sort of setup. So we have our point, down here is our point, A, B. So when we look at our slices, what's going on? Well, suppose we take a look at our slice. Let's look at this slice right here. Well, what's happening? Well, this is the slice which corresponds to y equals b. And if we plug in y equals b into this equation, notice that that part goes away. And so we get the following: f of ab plus f sub x ab times x minus a. And that is the tangent line. In other words, when we slice our tangent plane, we get our tangent line in the cross section. Of course, not very surprising. You might say, well, what if we did it the other way? Okay, yeah, we can. So if we slice here, which corresponds to x equals a, well, what we'll get is we'll get this cross section. And if you plug in x equals a, the f sub x term goes away. You get z as f of ab plus f sub y at ab, y minus b. In other words, you're recovering the tangent line in that cross section. This really meshes with our understanding of how partial derivatives work. Partial derivatives are telling us rates of change of the curves in our cross sections. In other words, they're telling us how do we make our tangent lines. So this is really wonderful. And so the moral is, once we've taken these different cross sections, we say, aha, what's happening is we have our one tangent line here, we have our another tangent line here, and therefore we put them together and we get our tangent plane. And so that's our idea. So now we can do tangent planes. We can find them, we can use them, we can explore with them. And if that were just all we were going to do today, that would be a great day. But wait, if you act now, we'll throw in a little more. So we're going to look at something else, and that's going to be the chain rule. All right, well, what is that? Well, chain rule is when you have functions inside of functions. It's one of the most important rules when it comes to derivatives. So we're going to do the same thing. We're going to talk about functions inside of functions when there's lots of inputs involved. So what we can do is we can do the following. We say, all right, we can say, for instance, we'll start with a very special case. But oftentimes, once you see how one case works, it generalizes fairly straightforward. We say, look, z is a function of multiple inputs, x and y. But x is some function of t, and y is some function of t. So we can talk about a hierarchical diagram. How do the variables relate to one another? So we say, look, z is a function which depends on two things, x, y. x depends on one thing, t, and y depends on one thing, t. And now we see how it all fits together. I will tell you that there are people who prefer to do their diagrams in a slightly different way. So depending upon where you look, you might see it written in this way. Z depends on x and x and y depend on t. It's not bad. Whatever you're comfortable with is what you should use. I prefer this relationship. Okay, so what's the idea? We want to ask the question, how does z change as we change t? Because if we look, what does z ultimately depend on? Well, the answer to what z depends on is what's at the bottom. Whatever variables show up on the bottom, that's what it depends on. In our case, there's only one variable showing up, so it depends on one thing, namely t. So we ask ourselves, okay, well, as we change t, how does our function change? That's a very reasonable question. So we say, let's start with our linear approximation. And this just comes from what we did before. And we say, look, we can rearrange, say, our change in our output, f of x, y minus f of ab, is approximately our partial f partial x at ab, which can be denoted as partial z partial x, times x minus a, which is change in x. Partial f partial y at ab, which is partial z partial y, and we're talking rate of change of z with respect to y, times y minus b, which is how much change is there in y. So if you divide everything by delta t, delta z divided by delta t, change in z with respect to t, in other words, what we're trying to figure out is approximately partial z partial x, delta x over delta t, plus partial z partial y, delta y over delta t. And now you let delta t go to 0, and what happens? Well, your approximation gets better. So instead of the squiggly lines, we get equals. And what happens? Well, we're talking about changing our output, changing our input. That's the derivative, dz dt, is partial z partial x, dx dt, partial z partial y, dy dt. Now let's pause for a second here, because you might notice we're mixing the partial and the d. When do we use which one? So why do we use partial in some places and d in other places? So it comes down to the question, how many variables are involved? So you notice z is multivariable. It depends on two inputs. So that's why, since it's multivariable, it's going to have a partial symbol. The partial is whenever you have something which has more than one input it depends on. On the other hand, you see that x and y and ultimately z, when we go all the way down, are functions of one variable. So when it's single variable, we use the d notation. So that's the only difference. D versus partial comes down to single variable versus multivariable. And it's kind of interesting. And the way I like to think of it is I like to chase through the diagram what's going on. So I want to ask the question, how does z change as I change t? And the answer is, well, it has two things going on. So what I'll do is for every time t shows up anywhere, I'm going to go down the diagram. So however many t's there are is how many terms you're going to get. And you say we can isolate them. So in other words, we can do each one individually and add up the net results. And what I like to do is, at least mentally, if I don't always write it down, is say, look, here z depends on x, so I can talk about how does z change with x. So this edge talks about how does z depend on x corresponds to partial derivative. Here, partial z partial y. Here I have y depending on t, that's dy dt. Here x depends on t, that's dx dt. And so, for every time I have a t, I have to connect. And so, as an example, I say, well, look, there's this t here. So I'm going to go down. And I say, okay, there's a partial z partial x, dx dt, and I'm multiplying them together. And then there's another t. Okay, what do I do there? Well, I do something very similar. So, all right, and then for the other t, I go the other route. Partial z, partial y, dy dt. If there had been 3 t's or 4 t's, just every single t, I just follow the chain down, and I just multiply what I see, and that gives me my net effect. In some sense, and this is of course a very dangerous thing to say, but we're among friends, so we'll talk about one thing that you might notice. It's like, look, here I'm talking about how does z change with respect to x. Here, how does x change with respect to t? It's almost like these x's cancel out. Not quite true, but it's not a bad idea. So we say, oh yeah, so this is how z changes with respect to t through x is the way we should see it. So we say, okay, the x changes cancel out, and we're left with z changing with respect to t via the route of going through x. And like I said, there'll be interesting cases. We'll definitely do some interesting cases as we go on. Well, what can we do with our chain rule? Let's jump over for a second and remind ourselves something which we've done before, at least in single variable calculus, explicit versus implicit functions. Now, an explicit function is one where we say, look, there's absolutely no confusion what's going on. We have z equals, and there's a nice rule. So we know the machine. In other words, if we were to think of our functions like a good machine, so we have our function here, then an explicit function is one where it says, look, I can actually open the machine up. I can open the machine up and I can look at all the various wheels and cogs and I see how everything fits together and moves through it and the computation gets carried out. That's an explicit function. So it's like perfect. I can just go in and if I ever want to understand it, I just take a look inside and I'm great. I'm good to go. But an implicit function, it's a little bit different. So it's one where we can't solve for z as a function of x and y, or x as functions of y and z. We can't get the variable by itself. And in that case, what do you have? Well, you may have heard something called a black box. And so what is that? Well, it's a mysterious thing where, look, we don't know what's happening on the inside. We're not allowed to peek in. So in other words, we don't know the actual formula, but somehow there's still a relationship. So when you plug something in, something still comes out on the other side. And so we're like, okay, there's something going on here. So it stands to reason that I can ask the question, well, if I'm changing x or if I'm changing y, what's happening to z? So that's what we want to do. We want to say, okay, how do we go about doing that? Now, initially, when you think about this, you might say, well, how could we possibly succeed? Because we need to take derivatives. We have to have the machine, right? We have to be able to look at it. And so we have a nice little idea. It's a wonderful idea, really. And it boils down to the following. We look at it and we say, what we're going to do is we're going to say, look, I don't know what z is, but I'll pretend like I do. So I'm going to say, I don't know what's inside that black box, but I'm going to act like I could. So I say, okay, regardless of what is actually there, I'll say, aha, I can do it, and I'm going to always think of z as a function of x and y. And now we're ready to go. Because what can we do? Well, what we can do is, what's happening is if we do think of z as a function of x and y, what we have is that both sides are expressions ultimately depending only on x and y. Right? Because z now depends on x and y. And since both sides are ultimately functions of x and y, we say, great. if we take the derivatives of both sides, either with respect to x or with respect to y, I'll get the same thing. Because if two things are equal, their derivatives also have to be equal. It's a fun idea, right? So now we take the derivatives, both sides, and we're good. There's just one small thing, which is whenever we take a derivative that involves z. Well, what do we do with that? Okay, well, the answer is we say, look, that's really partial z partial x, or it's partial z partial y. So let's actually get into what's going on. So we have the following, and we're going to do it very abstractly. Once we go into our practice, we'll go through and do it more concretely. This is why it's good to practice. Practice helps cement ideas in our mind. So we're going to start with some equation, and let's assume that we have f of x, y, z equals 0. In other words, we just took everything and moved it across to one side. Perfectly fine, we can do that. And remember, we're going to think of z as being a function of x and y. So we put on our little thinking hats and we're like, z is a function of x and y. We may not actually write it out, but we'll think it. So we say, okay, what can we do? Well, we're going to take the derivative of both sides with respect to the same thing. So remember, I'll actually write it out this time, just so that we can see what's happening. I have f of x comma y comma z of x comma y equals 0. Okay. So our function is what? It's a function of f depends on three things, x, y, and z, but z depends on x and y. Okay, so now we take our derivatives, and we say, well, suppose I want to take the derivative with respect to x. Where does x show up? Well, if we look at the chart, it shows up in two places. So I'm going to have two terms. There's this derivative, which I can call f sub x. Then there's this derivative, f sub z. And there's that derivative, which is partial z partial x. All right, so working down, we have f sub x plus f sub z partial x. So that's the derivative with respect to x of the left-hand side. Has to equal the derivative of the right-hand side with respect to x, but 0, it's easy to take that derivative, you get 0. And now we rearrange, and we come to the conclusion, partial z partial x is negative of the function, take that derivative with respect to x, divided by the function taking that derivative with respect to z. Doing the same thing, but with respect to y, not much changes. The only thing that changes is now we do fy plus f sub z partial y. Again, equals 0. So you can say partial z partial y is minus f sub y over f sub z. So these are kind of formulas to find the implicit derivatives. I actually prefer just to remember the rule. The rule is think of z as being a function of x and y and take your derivatives. And if you can remember that, you're great. Good to go. You can solve pretty much anything, and life is good. So, well, there was a lot we did today. We talked about tangent planes, we talked about chain rule, implicit differentiation, we threw in the ideas of differentiability, linear approximation. That's actually almost like a couple weeks of what we normally do in single variable calculus in one day. What a day! But if you're comfortable with the ideas from single variable calculus, you'll see, okay, there's a lot of the same ideas with just a little bit of extra added in. So it's not so bad. And it isn't. And as you go through the practice, you'll say, okay, this is actually pretty fun. Well, I think it's now time to go and do some practice. So, see you soon.